So this is question number 19 from electric current in conductors from HC Verma. And the question is very easy, but something that I would like to tell if you do the question a bit differently. So let's get into the question first. The question is there is a battery that's being charged. It's a non-ideal battery being charged by a charger. Let's just assume it's another battery that's charging this battery. And this battery is providing a potential difference of 9 volts. This battery has in itself an electromotive force of 6 volts, and uh, of course, we have taken the thermal energy outside. So this is can be taken as an ideal battery in itself. We've taken the resistor out. There is no thermal energy being produced. Let's say the resistor has a resistance of 4. Now the question is, when it's completely discharged, the resistance of this is 10 ohm. When the battery is completely discharged, it's completely used. But when the battery is completely charged, the internal resistance decreases to 1 ohm. So this is when this battery is discharged or used. This is when the battery is charged, okay, or used. Now we have to find the current through the battery. You can say just this battery or the whole thing. The current will be the same just after the connections are made. That means it's a discharged battery, but we are being charging it, but it's just at the point of time we have started charging. So there's just 10 ohm is the resistance that we will take since it's not charged, just plugged in. So it's discharged till now, till 0 seconds or 0.001 seconds. Okay, if you go by the loop law, it's quite easy. You have a voltage uh, gain of minus 9 volts. It's a gain, so potential rise is negative, and we have a loss of 6, and you have a loss of what? IR. So it's 10. Okay, and it's 0. So you take it to that side. I10 is 3 and I is zero point 0.3. So it's quite easy if you do it this way, and that's how it's done. I'm going to this the part A, and the part B is when it is completely charged, find the current. So you will go through the same process. Minus 9V plus 6V plus I. Now we'll use 1 ohm is equal to 0 since it's completely charged. I 1 ohm is equal to 9V minus 6V. That's 3, and I is going to be 3 amperes. Right? I think zero point 0.3 and we are the answers. Yeah. Now, what's the other way? Why am I making a video of this? Such a bad question. A bad question. See, uh, I'm just making it for you to know that a battery is a non-ohmic device. Why am I saying that is, let's just say one thing. Let's take mm, this as a part of a circuit. We know that since this is giving, let's say this is 9 volt and this is 0 volt. And so since this is providing a potential difference of 6 volts, this battery, 9 minus 6 is 3. So the potential is 9 minus 6, 9 minus 3 is 6. So 6 volt potential difference here. And it gets a 3 volt potential difference here since find the potential of this part of the wire is 0. So 9, 3 and 0. Now, for this part, if you use the equation, the famous equation, the Ohm's law, V is equal to I. You know the potential difference between these 2 points. It's 9V minus 0. So it's 9 volt is equal to I. The current through both the thing will be the same. And the resistance is just R, which is initially 10. See the measure here, it's 10, and so the current gets to be 0.9. And if we take it as 1, for the second case, we get 9. So what's wrong in this argument? Why is this 9 volt equal to this 3 plus C? I'll tell you why we cannot use. See, you can use these arguments if you had two resistors, like if you had two resistors connected in series, then you could have said that the total potential difference across it, 9 volt is equal to the current through all of both of them, that is I, and the equivalent resistance, that is R plus R. Completely fine. Completely fine. There's nothing wrong. But something goes wrong when you use a battery. That is because of this thing's derivation. If you see the derivation, for a part of C, V is equal to IR is just designed for an element of a circuit. We use it for some elongated part by a derivation. And this is basically a simple derivation that goes something like this. The current is same. Let's just say it's not tau. Let's just say that current is I. It has a distance of small r. It has a distance of capital R. The potential difference across it will be by Ohm's law IR. Across it will be by Ohm's law I capital R. Total potential difference is their sum. So I R plus R is the total potential difference. So we can use R plus R as R equivalent. So I R equivalent is the change in potential, or I is equal to the change in potential upon R equivalent. That's how it goes. If you have a battery, however, something like this, let's say the battery has an electromotive force of E, because it's an ideal battery now, because the resistance is removed. Now, if you try to derive the whole thing, you can say the potential difference across this part will be IR, but across this part will not, this E will not be IR. You'll say why? Of course, if you are just talking about this lonely battery, current is passing through it, it's an ideal battery, so resistance is zero. That means electromotive force must also be zero. What? What just happened? No. See, a battery is a non-ohmic conductor. You cannot use electromotive force is equal to IR, and of course, R is zero if you take an ideal battery. Even if it's not an ideal, you take the resistance over and now it becomes an ideal battery, and you cannot use. But wait, I have used E is equal to I a lot of times now. I know you have used it a lot of times, but the situation is different. See, when we use it in the normal conditions, for example, what the condition is usually is, well, let's say you have some kind of a circuit like this, then battery of electromotive force E, and you have the potential difference between it. It's an ideal, let's just assume. Then you can use E is equal to I R equivalent. Now, why we can use it here and why we cannot use it here? Oh, so let me just tell you. When we talk about these 2 points, let's say A and B, the potential difference between A and B is E. But this IREQ is not referring to the current inside the battery. This IREQ basically means the current is going from here to here. It's not going from here. Battery is not being charged, it's being discharged here. Current is going from here to here. And all the conductors that you see from here to here, I'll just highlight them. All the conductors that you see from here to here are ohmic. These are standard resistors that follow the Ohm's law. at least in theory. These are resistors that follow the Ohm's law, and hence we can derive it the same way I derived it here, like IR, I capital R, and IR plus R. So we can use, and this electromotive force is just telling the voltage, the potential difference. This E is just telling the potential difference, but we are not using the Ohm's law for this battery. We are using the Ohm's law for the circuit. There's a difference. This battery is just telling us the potential difference, and we are using the value of the potential difference to calculate the potential difference is equal to IR of the circuit. And the circuit has all ohmic conductors. But here we are using Ohm's law to calculate the potential difference between this battery. The current is going through the here also current is going through the battery. It is going from here to here. But we are not talking about the current that's going. We are talking about the current that's going through these ohmic things. These ohmic conductors. Of course, wires are taken ohmic and the resistors are taken ohmic. This battery, my friends, here, since we are considering the current going through the positive terminal to the negative, just talking about this lonely thing, then the electromotive force will not be equal to IR. Of course, you can say यार R की तो कोई वैल्यू है ही नहीं आइडियल है तो मतलब इलेक्ट्रोमोटिव फोर्स जीरो थोड़ा ना हो जाएगा. अब सही बात है ना, जीरो थोड़ा ना हो जाएगा इलेक्ट्रोमोटिव फोर्स अगर I जीरो है. तो फिर ऐसा कर लो, इसके अंदर जो करंट है वो E बाई जीरो इन्फिनिट थोड़ा ना हो जाएगा. आंसर में लिखा 0.3 है. इन्फिनिट करंट थोड़ा ना जाएगा इसके अंदर से, बैटरी के अंदर से. ठीक है. सो आई होप यू गॉट इट. When we are talking about just this lone battery, it's not an ohmic conductor. So the potential difference that's provided by this electromotive force, which is exactly the potential difference between these 2 points of the battery, it is, but it's not equal to IR basically because R is not. Now let's get to my question. See, since this is not equal to IR, see how did we get this 0.9 ampere? How did we get this? We said, well, the potential difference between these 2 points should be equal to IR between these 2 points. And how did we derive this? We said, well, the current through both of them should be the same like we had in two resistors. So I, and you have, let's say, R and R. So R plus R, which is R equivalent. But if you are using this formula and is a battery in between, it's a non-ohmic conductor. And I have, of course, proved you that electromotive force won't be equal to IR here. Because we're just talking about the battery. We're not talking about the circuit here. We're not talking about this part of the circuit from where current is going. We're talking about just this part of the battery. E not equal to IR. So you cannot say that the potential difference is अच्छा मैंने I के लिए I have used different variable IR, and you cannot say that the net potential difference is I, no, let's just take it as capital R, confusion हो जाएगी. So the net potential difference is, I R plus R. And then you say at last moment, yeah, resistance of battery is zero. Ideal battery hai. That means R is zero. Zero plus R should be equal to the potential difference. What the hell just happened? We took R zero, the potential difference आया ही नहीं. But anyways, at the last moment you decide यार resistance of ideal battery तो zero होते हैं. उसको चेंज इन पोटेंशियल से करेंगे जो कि 9 है, तो करंट आएगा आपका 0.9. Very good. That's why you cannot use because is not equal even equal to IR. So what do you have to use exactly? What do you have to use? You have to use, if you are calculating the electromotive force, it's not equal to IR, but the potential difference is exactly E or epsilon, whatever you say. So E plus IR, which is the net potential difference. I R plus R, where R is equal to 0 of a ideal battery is not the net potential difference. क्योंकि ये तो बराबर है ही नहीं. Epsilon, which is of course the potential difference between these two points, and IR, which is the potential difference between these 2 points. This is the net potential difference, which is equal to This is the net potential difference. This is equal to the net potential difference, or IR. No. Then you have E is equal to 0 again. No, 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 no. This E plus IR, which is the potential difference, is equal to the change in potential between these 2 points. If you have these 2 points, and this is 9 volt, which is given, the potential between these 2 points is 9 volt. This is equal to E and IR. But this 9 volt is not equal to IR. If you haven't understood why it's not equal to IR, then I'm sorry. I could not help explain it to you. This 9 volt is equal to E plus IR. The net potential difference is the net potential difference. Ohm's law is not valid because battery is not ohmic, because there's some chemical reactions going on. So you can also solve it this way, not by Kirchhoff's voltage law. E here is He given, plus IR is 1 given or 10 given, depending on part A or part B. So I10 is equal to 3, I is 0.3, or I1, which is part B, is 3, I is 3. So this was basically what I wanted to discuss. Here we can use, because here we're talking about the circuit, not about the battery. Battery is just giving the potential difference, which we are using for circuit. Here, just considering the battery, it's not an ohmic conductor, so it's not equal to IR. So it's not R plus R, and then you say at last, yeah, R of ideal battery is 0, then IR is equal to 9 volt, 0.9, and or 9 ampere, depending on party or copy. Because it's derived that both are ohmic. If you are saying that this part of the circuit must have a potential difference of delta V must equal to the current IR, is derived only when both the, or all the, if you have more than two elements, all the elements are ohmic. If they're non-ohmic, you cannot use that. And that's why if you have two batteries, it's just advised to use the Kirchhoff's formula. Just eat 5 star and use Kirchhoff's voltage law. Okay. Bye.